Good morning everyone, this is window presentation for our project for IDJ10803 Digital System 2 Semester 2 Session 2025/26. The title for our mini project is Elevator System. My name is PRIYASINI anak perempuan ANANTHA KUMAR and my teammates are KASHWINI and Anushavarthini. So the purpose of the project is to design and simulate a 7-floor elevator control system using digital logic concept. This project aims to simulate how an elevator responds to floor requests and moves between floors efficiently. It helps to understand the practical application of finite state machine, FSM, logic circuits and digital system design. Next, we can see few of the objectives for this project. Firstly, to design a 7-floor elevator system using sequential logic circuit, which is small circuit. Next, to understand the working principle of an automated elevator. Then, to improve understanding of digital logic design, flip-flops and combinational circuit. Lastly, to simulate the elevator control circuit using quarters 2 and reduce cost by using basic digital electronic component.
Good morning, I'm Kashwini, daughter of SHATTIASEELAN. For this project, we worked together as a team to bring our idea to life. At the beginning, we planned the system by creating state diagrams, state transition tables, and simplifying the logic using Carnot maps, which is KMaps. After finalizing the design, we collaboratively constructed and simulated the circuit using quarters 2. Finally, through consistent teamwork and effort, we successfully achieved the objectives of the project.
So this is the state diagram for this elevator system. So firstly, we can see that this state diagram is start from 0, 0, 0, which is ground floor, and x equals to 1, which means elevator moves up. If x equals to 0, it moves down. For this project, you can see that if it's 0, 0, 0, if x equals to 1, it moves to the next floor. If in 0, 0, 1 and x equals to 1, it moves to the next floor, second floor. So for example, if it's in 0, 1, 0, second floor, if x equals to 0, which means it's moving down, and it will go to the state 0, 0, 1, which means from second floor, it goes to the first floor. As you can see, these are the state diagram, and for the last state, which is 1, 1, 1, if x equals to 1, it remains that state, which is the 7th floor, because the 7th floor is the maximum floor. So if x equals to 1, it remains the 7th floor. Same as 0, 0, 0, the ground floor. If x equals to 0, it remains the ground floor. Next, we can see state and transition table for this project. So for present state, as I say, in ground floor 0, 0, 0, if x equals to 0, it remains, the next state remains the ground floor, which is 0, 0, 0. If x equals to 1, which means it's moving up, it goes to the next floor. If it's in ground floor, x equals to 1, the next state will be 0, 0, 1, which means it's moved to the next floor. It goes up and moves to the next floor, from ground to first floor. And next, you can see in the present state 0, 0, 1, if x equals to 0, it remain in 0, 0, 0, which means ground floor. If x equals to 1, it moves to the next floor, which is floor number 2, 0, 1, 0. So if present state is 0, 1, 0, x equals to 0, the next state will be 0, 0, 1. If 0, 1, 0, x equals to 1, the next state will be 0, 1, 1. And if it's 0, 1, 1, x equals to 0, the next state will be 0, 1, 0. If 0, 1, 1, x equals to 1, the next state will be 1, 0, 0. If 1, 0, 0, x 0, the next state will be 0, 1, 1. And then 1, 0, 0, x equals to 1, it will be 1, 0, 1, move to the next state. If 1, 0, 1, x equals to 0, it remain 1, 0, 0. If 1, 0, 1, x equals to 1, it moves to the next floor 1, 1, 0. If 1, 1, 0 equals to 0, the next state will be 101. If 110 x equals to 1, it moves to the next floor, which is the 7th floor, 111. And if the present state is 111, x equals to 0, the next state will be 110. And lastly, for 111, if x equals to 1, the next state will be 111. Now we can see Carnot map, which is K-map that we have done for this project, and the Boolean expression we got from the K-maps. After simplifying these K-maps, for J2 we got Q1, Q0 and X, and K2 is Q1 bar, Q0 bar and X bar. J1 we got Q2, Q0 bar, X bar, and then OR with Q0 and X. K1 we got Q2 bar, Q0 X, OR with Q0 bar and X bar. And J0 we got Q2 plus Q1 plus X, and K0 we got Q2 bar plus Q1 bar plus X bar. And lastly, we can see Y2 we got equals to Q2, Y1 equal to Q1, and Y0 equals to Q0. These are the Boolean expression we got for our mini project.
So this circuit is a sequential logic circuit designed using 3 JK flip-flops and several combinational logic gates. The JK flip-flops act as memory elements that store the current state, which is the present state of the system, and update their outputs when a clock signal is applied. The combinational logic, which consists of AND, OR, and NOT gates, processes the input signal X together with the present state from the flip-flops to determine the next state of the circuit. These logic gates generate the appropriate J and K inputs for each flip-flop, controlling whether the flip-flops set, reset, hold, or toggle. The outputs of the flip-flops are labeled as Y0, Y1, and Y2, which represent the output states of the circuit and are connected to FPGA pins for observation. So this is the waveform. This waveform simulation shows how the circuit behaves over time when different inputs are applied. In the waveform, the clock signal controls when the flip-flops update their states. Each time a clock pulse occurs, when the JK flip-flops evaluate their J and K inputs and update the outputs accordingly. The input signal X changes at different times and influences the combinational logic, which determines the next state of the flip-flops. As a result, the output Y0, Y1, and Y2 change based on the present state and output conditions. By observing the waveform, we can verify that the circuit transition between states correctly and that the outputs respond as expected with respect to the clock signal and input X. So as for the outcome, the project successfully develops a state table for a 7-floor elevator system. Each floor is represented by a binary combination of 3 flip-flops. The state table shows present state, which is Q2, Q1, and Q0 is current floor, input X, which controls elevator movement, and lastly output Y, which is representing the elevator state. Through the simulation using quarters 2, the elevator system can move between floors according to the logic defined in the state table.
So this is the pin we used in the E-Altera board. Clock is key 1, X is switch 0, Y2 is LED R4, Y1 is LED R3, and Y0 equals to LED R2. This is our output. So this is the key we used for clock input and Q2, Q1, and Q0. So when the input equals to 1, 0, 0 equals to 0, 0, 1. So when 0, 0, 1 equals to 0, 1, 0, then next 0, 1, 1, and followed by 100, and then 101, and then 110, and lastly 111. So when the x equals to 0, which means moving down, so 111 still remain the same, and then 110, and then 101. After that 100, then 011. So after that 010 and 001, and lastly it's 000. So that's all from us. Thank you.
For discussion, the elevator system operates using finite state machine model. Each floor is represented by a state in the system using 3 flip-flops. Since 3 flip-flops are used, the system can represent 8 possible states, which are 000 to 111, which are ground floor to 7th floor. The input x controls the direction of the elevator, which means x equals to 1, the elevator moved up to the next floor. When x equals to 0, it moved down. Based on the present state and input, the system determines the next state of the elevator. The state table also includes J-key values which determine how the flip-flop change state during transition. These values are used to design the logic circuit that controls the elevator movement between the floors. This project is important to society because it demonstrates how automated elevator system can improve the efficiency and safety of transportation within multi-story buildings. By designing a 7-floor elevator control system, the project shows how digital technology can be used to manage building operations effectively. The project also highlights the role of automation and control system in modern infrastructure. Elevator systems help people move quickly between floors, especially in crowded buildings such as office, hospitals, shopping malls, and apartments. In addition, this project contributes to society by encouraging the development of reliable and efficient control systems that can improve accessibility for everyone, including elderly and disabled individuals. Moreover, this project demonstrates the practical use of control systems, digital logic, and automation, making them an important real world application for engineering studies. In conclusion, the 7th floor elevator control system was successfully designed using a state table and JK flip flops. The system demonstrates how sequential logic circuits can control the movement of an elevator between multiple floors. By analyzing the state transitions and determining the required flip flop inputs, the project provides a clear understanding of how digital system can be used to automate real world applications such as elevator control. With the success of our project, we plan to aim higher. With our project as a base, our future plan is to create an elevator system even more better than the one we have created right now. Last but not least, as we look to the future, these technologies will play a crucial role in shaping a better world for upcoming generations. That's all from us. Thank you for your attention.